Hello students, welcome back to another lecture in our course Environmental Modeling and Simulation. In today's lecture we are going to talk about environmental transport processes. Some of these processes we have already discussed when we were deriving the model for air pollution in case of a stack, which is a point source for an air contaminant, air toxicant. We also discussed Fick's law, which tells us about diffusion, which is one of the transport processes in groundwater also. Today we are going to revisit those transport processes, both advection and diffusion, and we are also going to look at some other multi-phase transport processes which are very important when we talk about contaminant transport through environmental matrices and compartments. Now, one thing to notice is that when we do our mass balance or material balance and we conserve mass within a control volume, sometimes there are transportation processes happening within the control volume, let's say from one phase to another. For example, in case of dissolution of carbon dioxide from atmosphere into water, there is transportation of carbon dioxide that's happening from air into water or from water into air. And this is also transport processes which needs to be included in your mass balance. We'll go through these transport processes today, which you should be able to include in your mass balance. We'll start with diffusion. Now, simple diffusion at steady state, we already know follows Fick's first law. So, simple diffusion will follow the Fick's law, which is something we have used both in case of contaminant transport in air and in groundwater. So it will look like this, that the flux is proportional to the negative gradient of the concentration. Basically, the flow of contaminant is happening from higher concentration to lower. This is what we have already seen. And then we can add a proportionality constant, which is actually the diffusivity constant, which is a constant for the diffusion. Now this is the flux. So remember, the flux is the flow of your contaminant per unit area. So if you want to find out the net flow of contaminant with time, you might have to multiply this with area. Remember that this law is applicable only in case of steady state. So if you remember what steady state is when your concentration does not change over time. So when we are dealing with a non-steady state simple diffusion, so unsteady condition, then we use Fick's second law. Now Fick's second law looks very similar to Fick's first law because it has now time derivative to it. It will look like this, that the rate of change of concentration of contaminant I, so I here is your contaminant. Now this is important to note that we are using I for particular contaminant, because in your environmental compartment you might have multiple contaminants. So then you might want to say I is equal to 1, 2, 3 for them. So rate at which the concentration of the contaminant I is changing with respect to time is given by this. Di is the diffusivity constant for the given contaminant. This is applicable when we don't have a steady state. Now, typically in environment, because environmental conditions, we're typically dealing with large time scale, this is sufficient for us, the steady state condition. If you remember, even when we were deriving our Gaussian plume model for air contaminant coming from a point source, we assumed steady state condition, which is del C by del T is equal to 0, which is not always the case. But here, if we are dealing with a special environmental situation when we have unsteady conditions, remember Fick's second law. This is what we are going to use. Okay, now this is happening in single phase diffusion. So diffusion of a contaminant in gaseous phase into gaseous phase. So for example, in our chimney, when our stack was releasing a particular gaseous contaminant, it was releasing into air, so it was air into air, same phase. And in case of groundwater, we had contaminant flowing through the water, so it was water into water, again the same phase. But when we're dealing with multiple phase systems, then we need to account for the porosity of our solid phase. For example, in case of groundwater, we might have scenarios, let's say especially in the Weddell's zone, where we have multiple phases present together. For example, let's say these are soil particles. So we have solid phase, and these are not completely saturated. So some of it, they have liquid. Let's use another color to show some moisture. And then let's say our contaminant is this color. So some contaminant will be present in the liquid, some will be adsorbed to the solid, and some contaminant will be in the air. So now we are dealing with multiple phase and we are having diffusion here. So how do we take care of that? How do we account for diffusion when we have solid, air, and water, liquid, multiple phase system? Now for diffusion in such systems, we need to account for soil porosity and tortuosity. So then our formula looks something different. It will look like this, that the diffusion, so the diffusivity constant is what changes. So the diffusion through the pore will be equal to theta by tau, where d pore j, this particular term here, is diffusivity through pores filled with phase j. So j is your phase, and by phase, once again, it could be liquid. So for example, in case of groundwater in the Weddell's zone, so soil moisture basically, contaminated with a, let's say, a non-aqueous phase liquid, petroleum or something similar, then the water will be a liquid phase. Another liquid phase could be the pure contaminant in dry area. So phase could be liquid, it could be solid. For example, we are talking about the soil particles themselves or the gas. If you are interested in how the NAPL is diffusing through the gas within the Weddell's zone, between the pores of the soil. So d pore j, d pore is diffusivity of the particular contaminant through the pores of a solid media for a given phase, for the contaminant present in a given phase, will be equal to dij, which is diffusivity of a constant through a particular phase, multiplied by theta by tau. Now theta by tau are the properties of the soil, and they are porosity and tortuosity. So theta is the porosity, and tau, this is tau by the way, tau is tortuosity. So you need to account for both porosity and tortuosity of your solid phase media to find out the modified diffusivity constant. So let's take this example of a situation where we have soil and we have a water column above it, water column, and here we have soil, and we have some concentration of nitrates in the water, right? A relatively higher concentration of nitrate, Cw, in the water. And in this question, let's say example here. For this lecture, it's first example. So let's say the concentration of nitrates in the water, Cw, is given by 20 milligram per liter, which is quite high. And we know that the molecular diffusivity of nitrates in water. So molecular diffusivity of nitrate, ice nitrate in water, J, is given by 19 into 10 to the minus 6 centimeter square per second, right? This is for water. Here I is representing nitrates and J is telling me very clearly that J corresponds to water. And we know that in the concentration at a depth of 10 centimeters, so if you go 10 centimeter below, the concentration of nitrates in the sediment pore water, so pore water would be, let's say, given is 0.05 milligram per liter. So now notice one thing, the concentration of nitrate here in the water column is very high, 20 milligram per liter. Concentration of nitrate in the pore water at the depth of 10 centimeters is much lower, 0.05 milligram per liter. Remember Fick's law, things will move from higher concentration to lower concentration, so there will be net influx of nitrates into the pore water. So the question is then, calculate the diffusive flux of nitrates into the sediment. Now we know the diffusivity constant for water, right? So we know diffusivity constant for nitrate in water. This water is for water column, not for water in the pore, because water in the pore will behave differently because of porosity and tortuosity of the soil. So diffusivity constant of nitrate in water is given here. Clearly, we know that we'll have to find diffusivity of, because diffusion is happening into the sediment, we'll have to find this diffusivity of nitrate in pore water. So that will be the first step. Okay, let's first find out tortuosity and porosity. So let's say the sediment porosity is 65% and then the tortuosity factor is 3. All right, now we need to calculate. So first what we need to do is we need to find out diffusivity constant of nitrate in pore water, which will be given to us by diffusivity constant of nitrate in water multiplied by porosity divided by tortuosity, which is 3. Okay, how does that look like? So let's solve this now. Finally, we know that we have to find the total flux. So the total flux will be equal to J by area. Remember, flux is by area, which will be equal to some diffusivity constant del C by del X minus, to show the sign in which it is moving. This will be modified diffusivity constant. We have to modify it. So this will be given to us by D of nitrates in water column multiplied by theta by tau, as I discussed in the previous slide. And then here we have to find the difference between the concentration. So if you look here, the concentration in water is 20 milligram per liter and the concentration in the pore water is 0.05 milligram per liter, and the distance between them is 10 centimeter. That will help us with the concentration gradient. So now we have del C by del X. Del X is 10 centimeter, del C is 20 milligram per liter minus 0.05 milligram per liter. So let's put all this information. This value we know is 19 into 10 to power minus 6 centimeters square per second. The theta is 0.65, tau is 3, so we divide it by 3, and then CW del C will be given by C water minus C pore water, which is 20 milligram per liter minus 0.05 milligram per liter, and del Z is 10 centimeter, which is 0.1 meter. Now notice one thing here, I have multiple units going on here. We have centimeter here, we have meter here. So please be very careful when it comes to this. Make sure you're consistent in your unit. So for example, I might choose to stick with SI so that I have consistent units. So that's why when I put in the data in the equation, I always make sure that I write the units. So if there's any inconsistency, I can figure it out right away. Well, when you correct it for the units, using SI unit or using any other system of unit, the answer that we get, net flux of nitrate from water column into the sediment, is given by 3 into 10 to power minus 4 gram by meter square per hour. So again, if you change the units, your value might change a little bit, but this is diffusion. So to summarize, we looked at diffusion, simple diffusion at steady state, which is very simple, which we have used earlier. So I also gave you the formula for simple diffusion under unsteady conditions. So this is the case when del C by del T is not equal to 0. Now here's the fun thing. Fick's second law can be used to figure out Fick's first law. In unsteady state, del C by del T is not equal to 0. In steady state, this equals to 0. So this becomes equal to 0, which means this becomes constant, which is basically the constant flux. Okay, and the next thing we looked at was multi-phase transport. And in case of groundwater or any other multi-phase we have, diffusivity constants will change. We have to account for porosity and tortuosity. Now I'm going to look at dispersive transport, which is primarily advection. Advection is when the movement, the bulk action of the fluid itself transports a contaminant, and we have looked at it multiple times. In case of contaminants coming out from a chimney, a stack, point source of air contaminants, we said that the wind was the reason for advective transport. And very simple way to figure out the mass transportation was to multiply the velocity of the wind with the concentration of the contaminant at any given space. So with advective transport, this is a typical method that we use. The net flux will be given by Vx/Ci. Vx is the velocity in x direction, Ci is the concentration of the contaminant I. This will give you the next net movement. net flux NXI. Remember, this is per unit area, so if you want to find out per length or per meter cube, you just need to multiply with area or just make sure the units match. Okay, now we are going to look at advective transport again through a multiple phase system. So this is simple one phase system. Advection is happening in air. It's a gaseous compound, gaseous contaminant that we are tracking. This works perfectly. But what happens when we are talking about mass transportation, but there are multiple phases? So let's say this is the interface of the phases, and this is here we have gas and here we have liquid. Okay, there is a concentration of the contaminant in the gas and a particular concentration of the contaminant in liquid, and we want to see how they relate to each other. This is where boundary layer theory is used. So this is, let's say, a two film system. The actual interface between the gas and the liquid is shown by purple, and on the either side of this actual interface between the gaseous phase and the liquid phase, we have film. So we have a tiny film here of boundary layer and a tiny film, and they are of different widths. So this is XA. So let's say the concentration in the air is given by CAB. So CA tells me that it is a concentration of particular contaminant. Bulk, B is for bulk. So we are not talking about diffusion, because even if there is any heterogeneity within the gas, there will be some diffusion happening. But we are assuming that within the gas, the contaminant is well mixed. Same thing, within the liquid, the contaminant is well mixed. So this tells me B is for bulk concentration, A is for concentration in the air in the gaseous phase. So, and this line here, the straight line, is representing constant concentration, assuming that x-axis is talking about the concentration. So the concentration with height is constant, it's well mixed in the bulk gas. And then we have a thin film here, and here the concentration falls. This is where there is a small film that is formed, and by the time we reach within the air, we reach the interface, the concentration in the air becomes I. This is not bulk concentration, because you see within the film the concentration is slowly tapering away, and then the contaminant is transported. Remember, the contamination is being transported towards the liquid phase, and within the liquid phase, so the concentration at the interface in the liquid phase is CW. W is for water. Typically in environmental systems, our liquid is water, so we can stick with water. A is air, for example. Instead of using G, I'm using air, so we can be specific. I is for interface, by the way. So B is for bulk. I is for interface, concentration at the interface. C is obviously talking about concentration of the contaminant. A is for air and W is for water. Okay, these are the subscripts. So the concentration at the interface of the contaminant in the water phase is CWI, and then it drops further in the film, and here we have CWB, which is constant again. So in the bulk phase, it's well mixed, but there's a tiny interface between the bulk phase and the interface, a tiny film. That's where we have concentration gradients. So this is what happens when we are having transportation in multiple phase systems. So and now how do we solve this? How do we model this? So for this, we need to define some parameters, some constants. So let's look at some assumptions before we do the calculations. First assumption is that within the bulk phase, perfectly mixed, the gradient exists only in the thin films on the either side of the interface. And the next thing is that CAI and CWI are at equilibrium with each other. So basically CAI and CWI, their ratio is constant. So we can say CAI is equal to some constant KAW, which is in constant, equilibrium constant between air and water. So if we know CWI, we can find CAI. So this drop is determined by the constant KAW. So this is, let's say, our first equation. Okay. Now, since there is a concentration gradient here, we know that the flux will be dependent upon this concentration gradient. So the molar flux that will happen through the gas side can be written as J X I A. So here again, X is movement in X direction. So in this particular direction, I is happening at the interface, A is happening from the gaseous side, will be given by, remember, Fick's law comes into the picture, DIA, which is air, diffusivity of contaminant I in the air, AX, which is the area, and then we have concentration of gradient of the contaminant I by the distance. So this we can rewrite as DIA AX. Now let's look at DCI. In this tiny film, the concentration drops from CAB to CAI in the distance XA. So the concentration gradient can be written as CAB minus CAI divided by XA. So this is our concentration gradient. This is the flux of the contaminant coming from into the interface from the gaseous side. We can similarly write a system for what's happening in the liquid side. So in the liquid side, we'll have J, X, X is telling me the direction of the flow, I is the contaminant. On the water side is DIW, basically the diffusivity constant for the contaminant in the water phase, area AX into dCi by dx. Now if you go back to the slide, dCi by dx is basically the concentration difference from interface to here. So that will be given by, that we can rewrite this as. So notice one thing, I have not used minus sign here. Fick's law talks about minus sign because I'm not right now focusing on the direction. I already know that this is the direction I've understood. So the concentration gradient CAB to CA minus, I'm going to stick with the direction that I have selected. So we go from CAB to CAI, CWI to CWB. But yeah, you should use minus sign and proper direction. Okay, so we'll have CWI, which is concentration in the water phase at the interface, minus CWB, which is concentration of the contaminant in the water phase in bulk, divided by XB, which is the width of film on the water side. Okay. Now both the fluxes will be equal to each other. So JXIW will be equal to JXAW. So we can equate these two equations that we have, 3 and 2, we can equate them. And when we equate them, what we get is DIA, should put a comma here, okay. Now we can do this, we can equate them like this. Now one thing we need to do is, the area is same for both, so the area gets cancelled out. Now we can make few substitutions. So if you remember here, we had a system here, CAI is equal to CWI KAW. So that's one thing, we know that, we know the equilibrium constant, and we know that they will be at constant, CAI and CWI. So we can replace CAI with CWI KAW. So we have CAI, where's CAI? Okay, this is supposed to be CAI. So we can replace CAI with KAW CWI. Let's make another substitution. What we are going to do is we are going to introduce a variable. It's a hypothetical variable, and let's call it CW dash. It is the hypothetical concentration in the water, which is at equilibrium with the concentration in the air. So it makes our life much easier. So let's say CW dash has asterisk, CW asterisk, KAW is equal to CAB, right? Concentration of the contaminant in air in bulk when multiplied by KAW, which is the diffusivity, which is the constant, equilibrium constant air, water, is CW dash. So we are going to make this replacement, put it here. So CAB can be replaced with this, and CAI can be replaced with this. So now what we get is DIA KAW into CW star minus KAW CWI is equal to RHS. So one thing we can do is we can introduce another constants to reduce the number of constants that we have here. We can say that DIA by XA is equal to Kg, which is constant in gaseous phase. DIW by XW is equal to KL, which is constant in liquid phase. So one thing that I forgot to write here is that this is divided by XA and this is divided by XB. Okay, when we make these two new substitutions, so basically this is introduced as a new constant, and let's say this is because it's water, so it is KL, and this is introduced as Kg, G is for gas. Then we get our concentration of CWI is equal to KL CWB, which is concentration of water in bulk phase, which is very easy to measure, plus Kg KAW. Remember, capital KAW is the equilibrium constant between air and water at the interface, multiplied by this CW dash is equal to divided by KL KA minus Kg. So this is what we get. Now the net flux of the contaminant coming from one phase to the other can be some constant multiplied by the difference in the concentrations, which will be given by W minus CWB in the bulk phase. Now KL here will be equal to 1 by Kg KAW. So you can go from here to here very easily, it's just basic arithmetic, and this is your net flux. Alright students, this is all for today. In the next lecture, we'll look at the chemical processes that need to be included in your models. Thank you.